Okay, folks, welcome to Lecture 1 of Unit 5, and today we'll be talking about the atomic models, giving us a basis behind what this unit is going to be talking about. So why don't we get started right away here and look at some early thoughts about matter. And we're going to go back to the time of Aristotle, and you maybe remember Aristotle from Unit 1A, and making some observations about wood burning in a fire and seeing the ash and the steam that came off that fire. He said that nature and the things that make up nature consists of four what we called elements, and they were air, earth, fire, and water. And what separated one substance from another had to do with a combination or the amount of these substances that were in that form of matter. And we kind of funny, we kind of look at these nowadays, and these are early thoughts, and any of those elements, or what he referred to as elements, actually in our definition of what an element is nowadays, would not be considered elements at all. We know from before that air and earth are what we would consider mixtures, and water is a compound, and fire is just a form of energy. So, again, even though these are incorrect, these were early thoughts, and these are things that kind of held true for a while until about the time of Democritus, who was the first person to actually say that matter was made up of small indivisible particles called atomos. And if we look at that word atomos here, we can see that it's kind of where we get the word atom from, and being that we have these small indivisible particles, each particle was characterized by its size, its shape, and its motion. So Democritus kind of gave us the first idea of what matter was made of as far as these small particles. And that held true for a few thousand years until the time of John Dalton, who was an English chemist in the late 1700s. And what Dalton did was piggyback off what Democritus said, and saying that matter was made up of these small, solid, indivisible spheres. And he said that atoms of the same element have what he referred to as the same predictable mass. So if we had a piece of gold or we had a piece of silver, every atom in that piece of gold or every atom in that piece of silver had exactly the same mass. But if we compared the atoms of gold to an atom of silver, that they would have different masses, and that's what separated one substance from another. But he also came up with this idea of how when atoms combine to make compounds, and compounds like water, they form whole number ratios, and they're always going to stay in those ratios. And that's something that we hold true today when we look at 2 hydrogens to every oxygen for the formation of water, or we look at 1 sodium for every chlorine in the formation of sodium chloride or salt. And you can see on the right hand side how we have that small indivisible sphere of Dalton's model, the atom. So that held true for a while until the time of J.J. Thomson. And if you take a look over here on the right hand side, you can see some of the differences that we have with the Thomson model versus that of the Dalton model. And Thomson's model is referred to as the plum pudding model, and being that they were in England, plum pudding was very popular. Nowadays we don't really kind of look at plum pudding being a popular type of thing. So I like to refer to this as what we would want to call we would call this the blueberry muffin model, and I'm going to actually add that here. So we're going to say blueberry muffin. Alright, so the blueberry muffin. And the reason I call it the blueberry muffin model was because in the Thomson model here, he said that the atom itself was a positively charged solid sphere, very much like what Dalton said, and that would be the muffin part of our blueberry muffin. But interdispersed, spread out throughout that muffin, were these negatively charged particles, alright, not referred to as electrons at the time, but found that these atoms have these charged particles, and the atom itself was positively charged and with these negatively charged that were throughout the atom. And this kind of gave us this first idea that atoms were made up of actually smaller particles, what we refer to as subatomic particles. So again, if we kind of look at what the name of the atom means, or what atomos means, indivisible, it actually means that we can break these apart. So now we have this idea of smaller particles than that of the atom. And he discovered this through something called a cathode ray tube. And you're going to see a link pop up here in a minute where you can check out a video talking about the cathode ray tube and how light was influenced by a magnet. Alright, so the next model we want to look at here has to do with, our brain break. I just forgot. Anyway, why don't we get up from our table here and maybe get the blood flowing, maybe do a few burpees. And today's Chuck Norris fact of the day: there is no control button on Chuck Norris's computer. Chuck Norris is always in control. Alright, so moving on here, talking about our next model, and the Rutherford model. Now, if we take a look over here on the right-hand side, we do have a difference between what we had before and what we have now, because now Rutherford was kind of going against what Dalton and Thomson said, and he said that the atom was no longer a solid sphere. It was mostly empty space between the electrons. At the time, the electrons were discovered, and that these negatively charged particles, alright, were found outside the nucleus. And he said that this idea of a nucleus, this center part of the atom, had a positive charge and contained most of the mass of the atom. It would be like when you went onto a scale and a fly landed on top of your head. That fly would actually add mass to your overall weight, but it really would be negligible because it's so small. And he said the same thing here about the atom. Most of the mass of the atom is located here in this nucleus, this positively charged nucleus, but the electrons that were on the outside, and they were so small that they really didn't make a difference. And it's kind of an example of, if we had to look at the size of the atom, it would be like having a marble in a stadium, where the marble would be our nucleus and the stadium itself would be that empty space of where you could find the electrons. So our next model here is the planetary model, and this is something that you probably are familiar with if you've looked at this in terms of the atom. And the Bohr model here said that we had protons, which had a positive charge, and neutrons, which had a neutral charge, and they were contained in the nucleus, very similar to the way Rutherford looked at his model. And he said that electrons, though, which were on the outside, orbit the nucleus in fixed levels, very similar to the way that planets orbit the sun. So you can see here we kind of have these orbits that these electrons for each atom would follow, and that each of these orbits had different energy levels, and the further away that you got from the nucleus, the higher that energy level was going to be. But when those electrons changed energy levels, and they had this ability to change energy levels, they gave off light, and Bohr referred to that as a quantum leap. And you're going to see a link up here pop up in a moment for you to take a look here at what a quantum leap was and how it works. And this pretty much held true, and we can still kind of, when we get an idea of what the atom is, this is a good way to kind of get our basis, or a basic idea of atomic structure. But the one that we actually use today is what we refer to as the electron cloud model, and this was devised by Erwin Schrödinger. And he basically said that with the Bohr model, the problem with the Bohr model was that the electrons were actually moving too fast. They were too small to be able to give their exact location. We didn't know that they had definite orbits and they had definite energy levels. So what Schrödinger said was, instead of saying the exact location of where these electrons were, we are going to give probable locations, and those probable locations were based on equations of probability, and they were referred to as being electron clouds or electron orbitals. So these would be probable spaces, mathematically calculated spaces or volumes that we could find the electrons. So we had an s orbital, which was spherical in shape. We had a p orbital, which was a bow tie in shape. We had a d orbital, which was like a four-leaf clover. And we had an f orbital, which was kind of two four-leaf clovers smashed together. And we had different atoms of different elements. We had different combinations of these orbitals. And again, these were just probable locations of where we could find the electrons. And when you get to your electron cloud lab that you'll be doing in class, you're going to be mimicking what Schrödinger said, is this idea of using probability to find the most probable location. And the more dense that we can fine or the more dense the cloud is, the better the probability it will be for us to be able to find that electron. So I hope you got a good idea of some of the basics about the atomic model, and there's going to be lots of examples for you to look at. And if you have any questions, please make sure you ask, and thanks again for watching.